Love it. All right, let's do a fun, quick little experiment, Sanjay. Imagine you are a journalist tracking the space based solar power market. And over the last 30 to 60 days, what are you excited about that the market is screaming from the mountaintops?
I think we're living in, once again, an energy crisis. The whole Middle East situation in the last weeks has really brought it even more to people's minds how dependent we are on secure, available energy, and how dependent some regions of the world are on access to that energy coming from outside and not having much control about that, and how it affects everyday people's everyday lives, the availability of that energy and that cost of that energy. So it is really timely that new solutions are being brought to the fore to address some of these long-standing dependencies and challenges we've had, which we've just never had solutions for, and patch fix each time we have a crisis. We try to solve it in the short term and then go back to that fragile situation, which then breaks again sometime later. So what we're seeing is, with the huge demand increase in energy and electricity that's needed for various applications, particularly data centers in the Western world, and this shock once again in being able to get energy just for today's needs, let alone the growing needs of the future. I think this is just making it more and more possible to be able to have conversations around what could be the solutions that actually solve this problem in the long term.
In a lot of the news that I see, the energy crisis, the energy problems that it's causing far outweigh, or seem to me to outweigh, the time spent on actually discussing the conflict, on discussing the diplomacy of the conflict. It seems to be very much about the energy problem of it, which I think says a lot about where we are and how we think about war.
It's kind of very selfish when you think about it. It's the how does this affect me, um, effect on the conversations, rather than what's really happening over there that's causing these secondary effects. But energy is so fundamental to our lives that any disruption in that, for whatever that reason is, we're immediately trying to resolve that situation of how do I get that energy, and sometimes missing, the deeper deeper root of the conversation. Why are we in this situation yet again?
Well, some people might say that once we solve the energy problem, then conflicts like this might not actually happen so much, because there are some people that say they're actually all a question of energy.
Yes, I would agree with that. The quest for resources, whether it's energy, whether it's minerals, other materials, has always been a reason for conflict on Earth. And so being able to access abundant resources, whether it's energy or materials, somewhere where we have to compete less for it, could and should lead to less conflict in the future. And this is why energy from space and also other materials, resources from space, is so compelling and attractive a prospect if we can access those resources.
Let's chew on this idea for a minute. So, candidly, space-based solar power is essentially a threat to every major power structure in the world. Have you thought about the entities that don't want it to succeed and why?
Is it a threat? It is initially going to be complementary and adding to all of the other energy sources that we have, because we are in a world of not simply trying to substitute certain sources of energy, but just have more of it and get it to whoever needs it when they need it. So while there will be some transition and substitution going on, I think for quite a while it'll be an addition to all of the rest. In the long term, definitely some will do better than others in the market, for whether it's for economic reasons, sustainable reasons, security reasons. We will see the mix of energy sources change over time. People can see that as a threat, or they can anticipate that, see where the world is heading, and seek new opportunities and reinvent themselves. and capture these new opportunities that are coming. So I guess the ones who would see it as a threat are those who want to keep their feet dug in the ground and never change and just simply stick with the status quo. But that's a choice.
When you were last on here, Sanjay, one of the stories that you told lodged in my memory and probably lodged our listeners' memory, and it might not be the story that you want people to remember, but it was very memorable. Beaming energy across a space, and you chilled some beer in a fridge. That was 2 years ago, long that 3 years ago was that
That
experiment
was in
carried out?
2022, so it's 3.5 years ago now.
What can you chill now?
We're gonna
How many
do
beers can you chill?
Yeah, we're gonna do a one up on the chilling of beers. So our plan is to have as our first major ground-based demonstration of wireless power beaming a 100-meter distance demonstration. So the one you're referring to, we beamed power over 36 meters. This was between ESA and Airbus and a company called Emerald. 36 meters and a couple of kilowatts of power in this kind of quite limited audience demonstration of power beaming. This time with TerraSpark, we really want to bring wireless power transmission out to the world. We're not interested in doing a scientific experiment and writing about it in some research papers, which nobody is going to read, but really show the world that wireless power beaming is a thing, that it works, it can be used in an operational sense. So our plan is to power a live music concert with wireless power for the first time. We are going to be doing the real MTV Unplugged.
Oh,
Outstanding.
come on. Okay, we need more details. So who's headlining?
So that's what we're working out. So hopefully the right people see this show and want to sign up to be the first band to be operating their stage, lights, music, and everything from wireless power beamed from 100 meters away, unplugged. So the idea of doing this is not just a technical demonstration, which is something we need to do to show that we in TerraSpark have that capability, but it will also show in a really visible way that people can see and enjoy the experience of a real practical use of wireless power.
Where's that going to be?
Yeah, and when?
Currently, we're planning to do this down in Portugal, where we have some excellent collaborators at the Institute of Telecommunications in Aveiro, just south of Porto. And we're working out the exact location, but it will be somewhere down there. And in terms of timeline, we're looking at the first quarter of next year.
Could you predict how, because I'm familiar with Glastonbury, for example, and they've got very different sizes of musical festival. Will this be powering everything? So musicians, fridge, food trucks, and could you give an ish prediction of the power which you will be beaming?
So this won't be a Glastonbury scale festival. Clearly, this is ultimately still a small demonstration. So we're looking at beaming of the order of a kilowatt of useful power, which may not sound like a lot. That's less than what operates your kettle, electric kettle. But surprisingly, you can run quite a few speakers and some musical instruments and a sound table with that amount of power. So we're looking at basically a relatively small audience, maybe 100 to 200 people in a smallish space. But this is not filling a stadium and doing a massive concert, of course. But it'll still be
Jeremy,
an experience.
maybe we should put the band back together. Jeremy, head over to Portugal. We can play.
Super exciting, Sanjay. I love the idea because it's like a very tangible, relatable thing when people see and hear the amps are on, the music's coming out. That's coming from the sun. Like that's coming from a beam power across from one point to the next and improving the technology. It's really interesting because a lot of other strategies are like, hey, let's get our stuff up in space and make it work. And it's got to be in space to do anything.
Can I ask a silly question? The chilling of the beer was 36 meters or something. You said 100 meters for this. So you've progressed 40 meters in 4 years. Doesn't seem like a lot. Why is the distance so short? Could you just not make that 100 meters 100 kilometers? What's preventing that?
Well, first of all, this is not the same team with the same technology that's doing this demonstration that did that demonstration back in 2022. So this is a new company, a new set of people. We've got to show our stakeholders that we in TerraSpark have put a team together that has the know-how and the ability to do wireless power beaming. We could have done a smaller test, of course, but we wanted to do something that was still significant on the scale of what others have done in the past. So we're not breaking any records in terms of distance. Others have done power beaming over that distance and even longer. Neither for the power. What we're really focusing on is in terms of the three important metrics for power beaming, which are distance, power, and efficiency. We are focusing on the third aspect here. We're trying to show very transparently as well to people outside, which is something that historically teams have not been very open about, how efficient that transmission is from the transmitter, from taking DC power in on the transmitter side, converting it to radio frequency, beaming it across that distance, collecting it, converting it back to electricity as DC on the other side. So that DC to DC efficiency is a really important metric when you talk about power beaming on Earth or going all the way from space down to the Earth. So we're trying to push that state of the art in terms of end-to-end efficiency higher than others have done for this scale of demonstration. So that's one thing. Now, why are we not going even further than that? Well, of course, you have to crawl before you walk and run, but there is a scaling effect on the hardware, on the size of the transmitter and the receiver that has to happen in order to beam power efficiently over longer distances. So yes, we could go up to 500 meters or a kilometer, but then we'd have to build everything much, much bigger in order to get that power efficiently transferred. And that will cost even more money, right? So we're kind of capital limited in terms of how much we can put towards the hardware development to do this demonstration at this time. Now, of course, in the future, as we raise more funds and we grow as a company, we will be doing larger and larger ground-based demonstrations, beaming from ground to an aerial vehicle or from a plane down to the ground, and then ultimately from space to Earth. But it is a step-by-step process in terms of developing the technology and the know-how to do that at increasing scales, but also raising the capital that's needed to do these bigger and bigger demonstrations.
Yeah, it's like you push something out, you test it, you prove it, and then you take that to the next level, and then the money becomes more locked in with what you're trying to do and is allowing the next step to happen, right? Because this isn't as easy as throwing some stuff up in orbit and making it all work. Like, this is a complicated problem that requires a lot of steps.
And financing is also a staged process. Especially when you go with private investors, you're raising a 5 million seed round. That's enough to get you so far, and you have to unlock a tangible milestone, technically and as well as commercially, to convince your investors and new ones to then allow you to raise additional funds to go to that next step. So sizing that milestone in both in time and scale correctly with the funds that you have and the time that you need to do it in to keep their interest is really important. You get that right.
Let's move into the other pieces of your phase plan here. So, based on my research, we're looking at some orbital stuff happening in 2027, and then moving into potential space to Earth stuff in 2028. Talk to us about this Dcube mission that you guys were recently kind of pulled into, and what they're doing, what you're doing, and why it's so important to space-based solar power.
Dcube, a German company that is building in-space manufactured solar arrays, they are launching their demonstration mission called Arrakis D3 in February next year to demonstrate their rollout solar panels that can be stiffened into a rigid panel in orbit, so using in-space manufacturing technology. Now, they're also very interested in power beaming and space-based solar power, so they've invited a bunch of companies who have power beaming technology to fly into orbit with them on their mission to demonstrate, to provide a platform for demonstrating in-space power beaming using various technologies. So 5 different companies from Europe and the US are flying on this mission in February next year, and TerraSpark is one of them. So they came to TerraSpark and asked us, are you able to provide a payload for this mission? And when they asked us, we didn't even have any engineers yet. And we said, hell yeah,
Yeah.
let's go for it. We
That's
can
the entrepreneurial spirit.
deliver in 6 months. Let's do it. So that's what we did. We raised some money from angel investors in order to get moving. We hired some engineers, and in January of this year, we were already making designs for this power beaming demonstration that we'll be doing next year. So we're going to be delivering the demo hardware in just over a month from now, so that they can go and integrate it on their spacecraft. So that's pretty sporty for a company that's just started to be delivering flight hardware for a space mission.
Is that so? Just to be clear, from in that, so that's essentially what you're doing in Portugal, but in which orbit? How high?
Yeah,
like, yeah, is essentially what you're doing in Portugal, but in orbit.
This demo in space will be a very short range demonstration, a very small scale short range demonstration of power beaming on the spacecraft itself. So we're not trying to beam power down to the ground. We're essentially doing a very similar experiment to what Caltech did in 2023 in orbit, where they put a kind of shoebox size system onto a spacecraft and beamed power over 30 centimeters with radio frequency to show that the technology they were building for space solar power works in space. So TerraSpark is doing a very similar thing. And we're going to be sending a shoebox size transmitter on the spacecraft, and we have a little receiver with a bank of LEDs on the back, and we're going to beam power from one side of the spacecraft to the other and light up this bank of LEDs, which will have a camera taking a picture of these LEDs, and we'll be able to see them light up in space as evidence of that power being transferred. So there's 5 payloads. There are 3 of them are going to be wirelessly powering with lasers, doing a demonstration with lasers, and 2 of them with radio frequency, one of them being TerraSpark.
Recently, we did a top 10 of the world's biggest space raises of 2026, and PLD Launch Systems were in that, the Spanish company. You very diplomatically kept saying spacecraft. Are you using PLD? Is this SpaceX? Could you say what that spacecraft is?
So Dcube are getting the bus from a company called Astro Digital, and it's going to be launched on a Falcon 9 rideshare mission. Yeah.
So does the physics change at all between the Portugal demo and the in spacecraft demo?
No. So the physics is the same, and it scales over distance. And that's exactly what we're trying to prove and convince people of, that remains true. As you increase the distance, you increase the size of the transmitter and receiver accordingly, according to what the physics asks you to do, and you can continue to transfer that power efficiently over that distance, right? And achieve that 80 to 90% capture of that power that you transmit from your transmitter can be received and captured by the receiver. So whether you're doing that at a half-meter scale on the benchtop, or you're doing that at a 500-kilometer distance from low Earth orbit, that physics is expected to scale. So, of course, nobody has demonstrated yet that kind of distance of hundreds of kilometers. And hopefully the Japanese will be the first to do that at the end of this year with their Oisama mission, where they'll be beaming power from space. A very small amount of power, but enough to be able to capture it on the ground and validate that the physics is scaling as expected. So the models that say for the size of transmitter that you're beaming from at this distance, we would have expected to receive X amounts of power on the ground, and show that is actually what we get.
It's like a ratio that can be scaled and said, if they can pull this off, we can change the math of the inputs and outputs, and it should scale as according.
Exactly. That's what it says. It's relatively linear. In fact, as you increase the distance, the idea would be to indeed have that that calculation of what power you would have expected to receive extremely inefficiently, of course, when using small transmitters over such a large distance, but at least as close as possible to the prediction, so that you can then say, had that transmitter been 10 or 100 times bigger, I know I would have received 90% of the power instead of, 0.1% or whatever small figure it will be. So that will prove that it's an engineering scaling issue, not a physics issue, in order to beam power efficiently over these distances.
Just a quick comment to you, Mark. Like these conversations that we have are so interesting in just we're getting this massive lesson on how big shit happens. Like in these phase steps, in these tiptoes from idea to execution. It's fascinating. I want to talk about the technology a little bit more. So you referenced RF. In our last episode, we talked about RF. We talked about lasers. There's something that I'm hearing about this near infrared.
Before we get to the near infrared then, because one of that difference between RF and laser, there seems to be a big confusion about the difference between those. Like, why are you using both? Why are you doing experiments with RF and laser on the spaceship? Could you walk us through the differences, why you're using both, and perhaps where, if you had to put all your money on one, where you'd put it?
Well, I put my money on radio frequency. I have already. That's what we're doing with TerraSpark. So there's different ways you can get energy down from space. So using lasers is one, and using radio frequency is another. There's a third way, which is reflecting natural sunlight with a mirror, and there are companies that are doing that as well. But typically, space-based solar power, it refers to sending directed energy in a directional way down to the Earth using either optical lasers or radio frequency, which is in the same frequency range as satellite communications, for example. What are the pros and cons of these two different technologies? Well, laser is typically done, well, it is light. That's what laser stands for. So it's done either in the optically visible range, so 400 nanometers to 700 nanometers, or you can go into the near infrared that you referred to, which is invisible to the eye, but still the correct wavelength of frequency to be absorbed by the solar panels on the ground. And in fact, with near infrared, it is even the solar panels, the silicon solar panels that are in use in solar farms today are even more efficient in terms of the absorption of that narrow frequency range compared to the broad spectrum of sunlight. So you typically get about 20%, 22% efficiency when you put sunlight onto terrestrial solar panels. But if you were to send just that near infrared frequency, then you can get a higher absorption efficiency there. So what are the benefits of lasers? Well, with lasers, you do have very compact systems to do the beaming and to do the receiving of the beam. So you can build smaller optical systems that can send a laser beam down, and you can have a smaller receiver to receive that beam because the light is very, very collimated. It's a narrow beam. So that helps you build smaller systems in space and smaller systems on the ground, which have benefits. Now, of course, the disadvantage of using light is that things can get in the way of that when you're talking about beaming power from space to the Earth, because you have an atmosphere. So clouds and weather conditions get in the way of laser getting down to the ground, and therefore it is not able to provide a continuous source of energy to us to a particular place in all weather conditions. Now, that doesn't mean it's not useful. If you have the ability to move that beam from one place to another, and you have the satellite far enough away from the Earth, you'll have visibility of quite a lot of the Earth below you, where there may be some clouds in one place, but no clouds in another, and you can move the power to wherever you have clear skies and receivers are on the ground. And in the case of lasers, optical lasers, those receivers are your solar farms that people are building all over the place to capture natural sunlight. So the company you mentioned, or the deal you mentioned earlier on by Meta that was announced earlier this week with Overview Energy in the US, that's the business model that they have and the approach that they're taking using near infrared lasers to send power down to solar farms. So why might you use radio frequency instead? So radio frequency has been what has been kind of looked at most closely over the decades since the 70s for space-based solar power, because it does offer this all-weather capability of beaming energy from space to ground without the restriction of weather conditions blocking that passage of that power. So if you choose the frequency correctly, not only does the atmosphere not absorb it, even clear sky, absorb that energy. When you have weather conditions, there's a very limited amount of absorption in those weather conditions, meaning you can provide a reliable energy service from space to a receiver on the ground 24/7 and every day of the year, season independent, weather independent. That's always been the most compelling reason for going for space-based solar power, that's enabled by using radio frequencies in that way, because of that capability to penetrate the atmosphere in all conditions.
It kind of removes the coordination problem too that you mentioned. If there are clouds around, how do you redirect the signal and move this and move that? And it's all the time on, always working, no limitations piece to the puzzle.
Yes, and of course, with the ability to redirect a laser beam, you do have that flexibility to move the power around. But definitely, there's a coordination. But it's also a flexibility that comes with being able to send power where and when it's needed, because you have, especially when you're talking about a grid which needs balancing, depending on where the users are and where the generation happens to be in that moment. Sometimes you do need much more power in one place than another, where power stations are brought online to provide that power when it's needed. You can have a directed beam that moves that around in a very flexible way, which is value added to the grid itself. So that's one of the unique characteristics of space-based solar power over any other energy source on planet Earth. Simply cannot move power wirelessly in this way across vast distances. We're talking about between countries and even between continents. Power can be moved by the same power plant in a high orbit.
Jeremy, in to build those US-UK relations, here's a little cultural nugget for you. So that surge in power in the UK, famously, whenever England play football. So you know that football has 2 halves, right? 45 minutes each way. Half time, 15 minutes. Whenever it's half time, there's a huge surge on the grid because everyone puts their kettles on because they want to make a cup of tea. And so they always have to be ready for that demand.
The kettle surge demand.
The kettle surge in England.
It's a real thing. I remember visiting a hydroelectric plant in Wales, and they were describing how the fantastic capability of hydroelectricity, when you open those valves, it can within seconds start to provide a huge amount of energy. So they've got the TV guide next to them. This was years ago when people used to watch TV.
Everyone's always watching Dallas, so it's the final episode of Dallas.
Came on. When EastEnders was having a break, that's when boom, they need to turn up the power station.
Man, what a way to think about demand spikes and such. So speaking
so just on that, it's an interesting thing. You talk about the speed of it. So hydro in Wales, if I assume space-based solar power would be a lot quicker than fossil fuels, for example, in generating that initial burst.
Yes, that's one of the plus points as well, that it has a dispatchable capability. You can switch it on and off, and you can move it within seconds, essentially by electrically steering the beam from one place to another wherever it is needed. As long as there's a receiver to receive that power, you can move it very quickly.
You've got something that's moving quick, nimble, new tech, and then you have something that's very cemented, tried and true, but also very bureaucratic. What are some of the legacy regulators saying right now about space-based solar power, and how are they thinking about incorporating it, or are they? Is it something? Are they saying anything at all?
Yeah, there's various forms of regulation that will apply here that we need to get get the folks aware of what is coming, and eventually get them on board. So there's spectrum regulation. So the people who manage the electromagnetic spectrum and tell you what frequencies you can use and which you can't. And then there's energy regulation as well. So what you can connect up to the grid, for example, and what properties it has, and how it's going to work, how it's going to affect everything else around. So there's various layers of regulation. There's health and safety as well, that we need to get regulators to sign off on, and environmental regulation as well for ground receivers in particular. So all of these are areas where we will need to get buy-in and licensing and permissions and approvals, which are today not in place because none of them had been foreseeing this application of beaming power from space. Even though this concept is 50 years old, it's been in the space industry, and it's been an idea not mature enough or not close enough to realization to warrant any of these regulators to spend the time and energy to think about, okay, how are we going to get this to work from a regulation point of view. But in the last few years, as the activity has been really picking up on this topic, companies, including when I was at the European Space Agency, we were already starting to try to get these conversations happening with the various regulatory bodies like the International Telecommunications Union, the ITU, for example, for spectrum regulation, where these regulations are set every 4 years. New regulations are set at these meetings that happen with these very irregular cadence, or regular but very, let's say, slow. So it's something that we need to think ahead quite a bit about, because it will take some time to get the permissions to use this, particularly as space-based solar power is going to be something that's usable and interesting globally. It has that capability to be an energy infrastructure, not just sending power from a particular satellite to one country, but to many countries as it flies over. So we need to think about getting regulation ideally at international level to allow these systems to be interoperable and avoid interference and messing anything up for existing users.
Correct me if I'm not understanding this in the right way. ITU assigns those frequencies to countries, or are they actually assigning those to entities and companies?
So they're assigned, when it's done at ITU, that's international, right? So it's for all countries in the world have to agree, and that's what makes it also challenging. But once that happens, that's applicable to everyone, and then national regulators can then follow that guidance and make country specific regulations which are compatible with that. But there's two separate things. There's the allocation of the spectrum for certain application, for example, telecommunications or radio navigation or radar. So there's different bands for these different purposes. And then in each country, they are responsible for deciding who's using which part of that band for that purpose. So within a telecommunications band, there can be lots of different companies using different parts of the spectrum, and that is licensed at the national level.
But so today, it would be like in the States, it would be like the FCC would handle that piece of it.
The FCC, and each country has its own regulator.
Okay, I'm not clear on this, so I'm going to read Jeremy's question that he prepared. When we first spoke, though, before that, we spoke about sovereign power sources, and one of the uses for space-based solar power might be a big data center. They need their own power supply. They don't have time to connect to the grid, or they're too far from the grid, or whatever the reason might be. They could have their own source of that beam down, and they could run it like that, which I think falls into the question that James was asking. So I'm just going to ask the question that he wrote down, so this will help me understand it. A Luxembourg registered company owns a satellite in LEO that is beaming power to receivers in Nigeria. What legal framework governs that transaction? Luxembourg space law, Nigerian energy law, ITU radio regulations, the Outer Space Treaty. So you covered some of that, but Could you just tell me the answer to that in one word?
So it's similar to data services, right? So we're like in SATCOM, where you have a country that launches a SATCOM satellite but delivers bits of data to different countries. Yeah, they have to get the agreement and license from each country where they're sending those bits down to, because they're using a particular part of the spectrum that's landing on that country. And it may be different for different countries as well, depending on their own individual regulations. But ultimately, yeah, they are a company, a global infrastructure that is having customers all over the world, Starlink, for example. So we would be quite similar in that way. In fact, also sending radio frequency down to different countries, but instead of bits of information, we are sending watts of power to receivers who are paying for those watts rather than bits. So I see a lot of parallels and ability to build on existing regulations and frameworks that allow transactions to happen that way. Now, because this is still an assumption, we have not got to the point yet of discussing that level of detail of how the implementation would be with different countries for those kinds of energy service provision yet. That will come. Right now, we're focusing on just the legal framework for allowing a certain frequency to be used to send energy and proving that it's not going to disrupt anyone else who's using frequencies there or nearby.
Yeah, it's the pathway. You're looking for permission to use the pathway, right? Kind of.
Yeah. And there's a couple of ways we could go. We could either try to secure a dedicated piece of the spectrum just for power beaming, which would be ideal, but extremely difficult, I believe, because all the spectrum is kind of spoken for already for existing usage. So trying to extract that out from existing usage and saying, okay, this should be for power beaming may be challenging. So the other option is to say, we'll use an existing part of the spectrum, but that's going to be fine because we are not going to interfere with anyone else. And how could that be? When we're talking about sending large amounts of power, it's because the characteristic of the frequencies that we are using is very different to telecommunications, because we're not sending any data. So we can use a very narrow frequency band, basically a single tone frequency without any bandwidth around it to send that power, which allows naturally non-interference with other frequencies nearby, because we are not doing communications and they are. So at least that's one thing that of how power beaming is done with radio frequency that lends itself to something positive and easier to deal with.
Jeremy, can you help me out with a musical analogy here? Because Sanjay said the word tone, and he also said the spectrum is full. Help me understand that with the musical analogy, because why is the spectrum full, and how would it, if you use the music analogy for tone, make it make sense?
Think about it as like there's different lanes on the highway, right? That cars can travel down, and the way
that's limited to how many?
Yeah, how many is limited, but it's also like if you have two communication pathways, like Sanjay is saying, one can interfere with each other. It's called like crosstalk, right? You could have crosstalk from one to another that, like if my signal is going down one highway and you're right next to me and my signal is too loud, I could affect the quality of the signal on your end. But Sanjay, does the power stuff we're not worrying about like TCP/IP when we talk about power beaming, right? Is there a difference that we need to think about?
Yeah, so this is not a beam that is encoded with any information. It's not modulated, right? So normally you're sending information down a radio frequency, whether it's for music on your car radio using FM or AM bands. That's modulating a signal with the information about the music on that modulated signal, whether it's frequency that's changing or amplitude that's changing. That's the FM or AM. And your radio is capturing that frequency, capturing that wave and extracting the information from the modulation that's on it. Now with power beaming, you're not sending any modulation of that frequency, and the receiver is just capturing that wave, that radio frequency wave, and converting it into DC electricity.
So Mark, my head goes to Willy Wonka. You remember the little section in Willy Wonka where Mike TV gets beamed from one section to another, where the chocolate bar is being beamed. So on the receiving side of the end, we're not trying to put Mike TV back together. It's just some power that's coming across, that's turning into something that doesn't have to be made into its original form. Is that close? Is that a dumb analogy? What do you think, Sanjay?
Yeah, I think that kind of works. Yeah.
I understand that. It's just more about the amount of tones in the spectrum. Like, if it's full.
Yeah. So when I said full, I meant not that it's all being used by people beaming frequencies in the entire spectrum, but the allocation of the spectrum. So this gigahertz of frequency up to this gigahertz of frequency has been allocated to different uses already. So in the ledgers of the ITU, they say that we've all agreed that 5.8 gigahertz to 5.9 gigahertz is going to be used for X purpose, right? Whatever it happens to be. Now, how many people are actually using it in that range in a particular country will depend on what services are being used in that country. So in the middle of nowhere, in a small underdeveloped country, that spectrum may be available because nobody's using it. Even though it's allocated for use for telecommunications, there may not be anyone actually sending those frequencies around because there are no services. And then another country like in the US or Europe, there may be 100 radio stations wanting to use that tiny band. And so they all have to make sure that they're not cross-talking by, within that country, getting allocated a sliver of that band for their particular radio station. So everything is being allocated for some kind of use or the other. And power beaming was not ever envisaged to be one of those uses. So it doesn't have its own place right now. So we either need to create a space for it, which means taking away from something that's already existing, or show that we can coexist with some other use case, whether it's telecommunications, whether it's radar or Earth observation, whatever it is, we show that we can coexist so that we don't need to have a separate allocation just for us. That could be an easier.
That could be an interesting plan. Could be an interesting planned future experiment when you're beaming, power from one side to another. You have some kind of data going across really, really close by frequency to show lack of degradation of signal. And that is that planned as a next?
Yeah, we've done that. Yeah, so we did that kind of very impromptu and ad hoc in that 2022 demonstration that we talked about before. Down in Airbus in Germany, while we were beaming this power beam, 2 kilowatt power beam at a power density of 500 watts per square meter, which is quite high, we flew a drone into the beam. Right, and this drone was operating at 5.8 gigahertz, which was the frequency of the power beam. And this drone's video, and that was for the control, and this drone's video signal back to the receiver was also at 5.8 gigahertz. And there was no impact on the control of the drone, no on the video's feed that was coming through. And this was commercial devices never designed to be sitting inside a 500 watts per square meter power beam at that same frequency. And it just showed us that systems that are designed for communication, where they're looking for a signal, a modulated signal, and extracting that data, can not mind that there is an unmodulated signal right there at that same frequency up to a point. Now, if you get to really high power levels, you have a risk that that carrier frequency itself can just put too much power in that burns some electronic devices. Now, this didn't happen in this case, but at least from an interference point of view, it showed that there appeared to be none. And one of the things I did while I was at ESA as well in the Solaris program was to initiate a R&D activity with a university in Portugal, one of our partners now with TerraSpark, to actively study how power beaming could avoid interference with, say, Wi-Fi and 5G signals. And they did a systematic study to show that showed that a power beam can coexist with these existing telecommunication uses without interference. And that was a very positive result that showed with experimental evidence that coexistence is possible. Now we need to do this with more realistic devices from different providers, consider SATCOM signals as well, not just 5G and Wi-Fi, and kind of broaden the scope of our testing to really gather that data to eventually present to regulators and the wider industry, who are all going to be naturally concerned about whether their operations are going to be affected by something like this, to convince them that, hey, look, we've looked at it, we've tested it, and it's going to be fine.
I got an idea for the TerraSpark Music Festival in Portugal. So you have the stage being powered. Yeah. So I've done some fun experiments related to latency in music and live performance and all of that. But you have the power beaming powering the stage, and then you could actually take the monitor signal, the signal chain from the stage monitor, back through a streaming mechanism and do like an audio live stream on it, or even a video live stream on it, in the same spectrum that you have the power beaming. And that way you could have this real time, hey, it's powering, but it's not degraded. It's kind of like what you did with the drone, but you could do it musically. It could be pretty cool.
Okay. We'll have a think about that. Yeah, that could be a real time non-interference demonstration as well.
Well, it's exciting. I love the updates, Sanjay. Thanks for joining us, and thanks for sharing about the TerraSpark Music Festival. That's going to be something pretty powerful. It has definitely press worthy. It brings the cultural side of what the world loves in music, and help demonstrate your technology. And man, the energy that you have now, the entrepreneurial spirit. You're kicking down doors, you're taking names, and we can't wait to see what happens in the future.
Yeah, thanks very much for having me on again. It's been a real pleasure to share with you, and I'm glad that enthusiasm that I'm feeling is coming through, because this is really exciting, and especially moving at this pace, it's kind of making my head spin, because it's just so liberating to be able to get stuff done like this.
Could we give you the floor for 1 minute? So the world is listening, the politicians are listening, the power brokers are listening, Joe Public is listening, my in-laws are listening, my friends are listening.
Pressure.
1 minute, Sanjay, no pressure, but sell them the space-based solar power dream, vision, future.
Well, this is not a dream. This is happening. This is next generation solar. That's all it is. Solar's absolutely wonderful. We're so lucky to have the sun give us all this energy. We're doing a fantastic job with capturing it now with ground solar, and we'll continue to do that in the future. But there are even better ways that we can get and harness this wonderful resource of the sun. And that's by putting these panels where the sun is most available, most intense, and most reliably providing us that power. It just so happens that it's very, very offshore, up in orbit. But at the end of the day, this is solar power that is going to be a big part of our future. It's going to be able to give us reliable, abundant power to be able to transition away from legacy sources and generate that power that we need in future to improve our standard of living for those that don't have enough energy, and maintain that for those already doing that today. So it's definitely the future. It's coming, and we need more people to be aware of it and talk about it and support it. And then we'll see that lovely sun juice coming down to Earth in a fantastic new way.
Sanjay Vijendran, TerraSpark, thank you for thinking on paper with us today. It's been wonderful. We'll stay in touch. We'll let everyone know what is happening. If you're listening if you've enjoyed this, if you've learned something, if you have spent an hour of your time thinking on paper about space-based solar power and you want other people to listen, please share this episode with 2 people today. 2 people. 1 person you like, 1 person you don't. And until next time, be disruptive, stay curious.
Keep thinking on paper.